sir, just one thing in the current part, if we have, let's say, a two input NAND gate, then what will come in the denominator?
Even then it will be 2. In a 2 input NAND gate, one of the PMOSes will be off. Suppose 0, 1 is the state of inputs. So one of the PMOSes is off, the other one is on, and one of the NMOSes is off, and other one is on. Anytime half the PMOSes and half the NMOSes are on and off, na?
Yes, sir.
Hai na?
Yes, sir.
Yeah. So there was a question as to what causes this leakage and so on. So there are multiple sources of leakage. The first and most important source is subthreshold conduction. What does it mean? It says that transistors cannot abruptly turn off. So it does not happen that as soon as you go below VT, transistor is completely off. We saw that IDS VGS characteristics. याद है आपको हमने एक log curve बनाया था, where we had talked about subthreshold slope and so on. And this is log. And we had said that the slope has to be 70 millivolts per decade and so on. You remember that? 60 millivolt per decade and all that.
Yes, sir.
Yes, sir.
Yes, sir.
Huh? So what
Yes,
we were
sir.
talking about there, we were saying that it is not that VT ke niche current goes to 0 at once. Okay, it reduces very, very significantly. There is a logarithmic exponential reduction in current as you go below VT, but current will still flow. And that is what is subthreshold conduction. Okay. Then another set of leakage is gate leakage, which is tunneling through ultra thin gate dielectrics. So even though we are now using high K metal gate dielectrics, which are physically not as thin as silicon dioxide based gates would be, but even then the effective thickness of the gate is the physical thickness of the gate is of the order of 2 nanometers or 3 nanometers, not more than that. In technologies where we do not have high K metal gates, in those technologies, because you want effective gate oxide thickness to be less than 20 angstroms, 10 angstroms, and so on, there is a lot of tunneling current that can flow, and that is what is gate leakage. And then we have junction leakage, which is that there are reverse biased PN junctions in our devices. So where all do we have reverse biased PN junctions?
That source to body and drain to body junctions.
Yes, source to body, drain to body, both are reverse biased junctions. And even though they are reverse biased junctions do also conduct some current. So that is where we have junction leakage. We will look into these in a little more detail and their impact on how we design. So subthreshold leakage, as we just saw, is the current that is still flowing after VT has, after your device has gone below VT. So this is what is defined as VT in this particular graph. And you see there is still some current flowing. Even at 0 value, there is some current flowing. So that is what we call as subthreshold current, IDS. In a very, very good transistor, this subthreshold slope would tend to 60 to 65 millivolts per decade. Okay. Why is this 60 millivolts per decade preferable over 100 millivolts per decade? We've discussed this part also already.
It is the best limit for silicon.
I'm sorry?
Sir, it is the best that silicon can achieve, and also
No, my question is not why 60. I'm saying why lower is better.
Sir, decade, the ID will decrease per decade.
Below VT, you want current to decrease faster.
Because current will reduce much faster. As you reduce the voltage, uh, there will be a decade of current reduction within whatever number we have. If it's say 100 millivolts per decade, then it requires 100 millivolts lower than VT to get 1/10 the current. Whereas if it is 65 millivolts per decade, it means my device has turned off very quickly, and even 65 millivolts below VT, I will have 1/10 the current. Okay, Faisal?
So I have a doubt in the gate leakage only. Why?
Yeah,
Why?
gate leakage will come at. Will come
So
at
why
gate
we
leakage.
were using the term tunneling? Actually, that's my doubt only.
Yeah, we'll come to it.
Okay. Okay, sir.
Okay. So is subthreshold leakage clear?
Just a very small doubt. So like when we were discussing the MOS capacitance and then we moved to there was when we were discussing the first time you told us about sub threshold, you were saying that one is that there is a depletion width under the gate, and then there is a depletion of the PN junctions of the source and drain. So somehow they get connected, and that is basically providing a path. So that is the path for that this sub threshold leakage. I mean, I just wanted to confirm.
Yeah. So let us go a little beyond what we were talking on in the last class also, or possibly in the last office hours, where we were discussing about availability of electrons in the conduction band. So do we realize that at all times at room temperature, there will be some electrons in the conduction band?
Yes, sir.
So if there's an electric field applied somewhere, those electrons will flow.
Yes, sir.
That is leakage. Even if the device is off, there will be something in the conduction band.
Okay.
Hai na?
So, but I mean, I'm not able to clearly visualize the path exactly. Though the band theory tells us me that there will be leakage because any time point of time there will be conduction electrons, but that path I'm was just clarifying about the path.
Yeah, subthreshold means source to drain path.
Okay, but that path is provided by the depletion connections. I mean,
No, not exactly. So depletion, definitely. Depletion region is a, so what is the difference between a depletion region and a regular substrate?
so I mean, depletion means that what the nature of that substrate was, you have avoid the excess carriers from that region, basically.
So in depletion region, all the excess carriers have been depleted.
Yes, sir.
So if you inject some electrons from one side, because there are no other carriers and there's an electric field across the depletion region, these electrons will move very quickly across the depletion region. That is one aspect. But there may not be a complete depletion region also formed there.
Okay.
Okay. So probably when we go into an accumulation mode, then we can say that there is a different kind of a current flowing, but depletion region ho sakta na bhi ho, and even then current would flow.
Okay. So because like I am able to visualize depletion region as a like very, very high resistance kind of region. I mean, its resistance are too much like greater. So that may be the limiting factor.
I can't comment.
Okay.
Okay.
Sir,
So yes.
yeah, in the first formula, can you repeat the terms in the exponential because I mean it's a little blurry.
The terms in the exponential are VGS minus VT naught minus eta VDS minus K gamma VSB. So you have all these things in the book available. Don't worry about it. I'm not going to ask you these formulae in the exams or any, and you will not be asked these formulae even in the in the interviews. Don't worry about that.
And so what's the difference between VT and VT naught?
Okay, so V capital T is the KT by Q component.
Oh, okay, right. So VT naught is just a subthreshold voltage.
VT naught is the threshold voltage at 0 VDS. Okay. So again, there is some issue. So we are saying that there is a subthreshold current that is flowing, and that subthreshold current is dependent on VT, threshold voltage. That is also, if the threshold voltage is lower, the subthreshold current will be higher. We are also saying that this subthreshold current is also dependent on the relationship between source and body, the body bias voltage that has been applied. We're also saying that the subthreshold voltage, this subthreshold current is also dependent on temperature by the virtue of this component KT by Q. As temperature increases, KT by Q also increases. So we're also saying that this subthreshold current is dependent on temperature. So when we say that the VT of the device has changed, what has happened is that if you, for example, you change VT from 0.4 to 0.1, the same curve, when it is shifted to the left, would intersect the VDD or the gate input Vin equal to 0 axis at a different place. And therefore you can have multiple decades of difference between a high VT, the leakage of a high VT device, and the off current of a low VT device. So this is just an exemplification that you reduced in 65 nanometers, as you reduce VT by 100 millivolts, you increase the off current by a decade, because we assumed that the subthreshold slope is 100 millivolts per decade. Okay. Now we come to some other effects which are slightly nuanced but are important. So one effect is drain-induced barrier lowering. What does this mean? This means that when I apply, when I change, so see, typically the leakage phenomena is dependent on gate pe kya voltage hai, what is the voltage at gate, and when it is off, even then some current is flowing from source to drain. Some electron flow is happening from source to drain. So that is your typical leakage definition. However, what happens? There is a voltage on drain and source also that is applied. And we see that there is a dependence of on current and off current, on current obviously, but also off current on leakage at VDD equal to 0. This happens because as you increase the drain voltage, the electric field contours change in such a way that in a long channel device, why is this happening today? Just give me a moment. So first tell me, you understand the difference between a long channel device and a short channel device? No.
Yes, sir.
So what is the difference?
Sir, we reach voltage, velocity saturation more quickly in short channel devices. So you have lower current, in saturation.
So, okay. So as the technology scaling happens, as you use shorter lengths, what starts to happen is that your device behaves differently than the standard, set of equations that we studied till now. Okay. This deviation in behavior is referred to as short channel effects. Okay. And why do these effects happen? We will look at it in this explanation that I'm just about to start with you. So let us say this is a big long channel device. And over here, I have a short channel device. Okay. Now, in a long channel device, let us say VD is 1 or 2 volts and VS is 0. So what happens? There is this barrier between drain and source. So there is a depletion width over here. There's a depletion width over here. And in between, there is a barrier. If I try to draw that barrier would look like this. So what is happening? This 2 volts that I had over here is dropping across the channel. So as I move from drain side to source side, this barrier is increasing. If I have a higher voltage over here, currents would be, electrons will be attracted over here. Now, in a long channel device, this barrier, so electrons have to jump from source into this region. So this barrier remains high. However, in a short channel device, what happens is that as drain tends to come closer, we see that the barrier reduces. When this barrier reduces, what happens? More electrons can now flow. So for a short channel device, let us look at it in a separate graph. For a short channel device, the drain and source are closer, and the barrier over here reduces than this value. So electrons can now more easily jump and reach the drain. This is called as drain-induced barrier lowering. This happens because over here we saw that depletion regions were far apart. Whereas in short channel devices, depletion regions actually start to come very close to each other. As they start to come close to each other, the barrier starts to reduce. Questions?
Sir, what is this? So is this some energy barrier or some physical barrier due to
Yeah,
depletion?
this is the energy, this is the conduction band that I have shown.
So here we assume that the depletion of drain and the source in long channel have reached their maximum depth, even if how much ever the VD is raised in long channel.
So the source and drain, this junction, this is the junction property. This is not, we're not talking about the gate over here.
No, sir, I am talking about, yeah, I am talking about this junction only.
Yeah, the junction to jo hi form hoga, there will be some depletion width form, and then we have this voltage applied, due to which this depletion would have changed already. Yes, we're talking about a static condition.
Okay, okay, so we are not in, okay. I thought that if we increase VD, maybe we can achieve DIBL in long channel also.
No.
No, never. Okay.
Sir.
Yes.
Sir, so this condition which we are speaking right now is in the is during my transistor is off, right, sir?
Yes.
So, sir, if my transistor is off, then obviously my depletion region would be above, because there is no inversion layer over there. I didn't understand why this depletion region moved a bit up.
Depletion region, there is no depletion region also here. Did I show a depletion region there?
No, but okay, sorry. Yes, sir.
Anna?
Sir,
you
so
said
where
that
is this depletion region we are getting from, sir, exactly? Is it due to drain and source?
Yeah, that is the PN junction.
Okay. Okay, sir. Okay. Thank you, sir.
Okay.
so you said that this is the energy conduction band diagram, but how is this a conduction band diagram? It looks like some physical structure.
So let me, if I simply move this, just give me a minute. Yeah. इसको हटा देते हैं. And so are you able to see this now?
Yes, sir.
Let me also put this here. No. Hello. Yeah. Are you able to see this?
Yes, sir.
That is what I'm saying. That's it. Because it's 2 volts over here, the overall energy is lower over here, and because it's high over there, this in fact the source would be since sources are 0, this energy would be appearing higher, but there is this barrier, and this VD over here, the change in depletion width that it causes does not impact anything on the barrier on the source side. Whereas when you apply a high VD over here, it causes a change in depletion width in such a manner that the source also starts to get impacted. And therefore the barrier reduces.
Sir, why did the VD become high, sir?
Because you charge the capacitor, na? In an inverter, you charge the capacitor to VDD.
Yes, sir. Yes, sir.
So you change the VDD, na? You change the VD, na?
Yes, sir.
Okay.
So
Yes.
even when the VGS was less than VT, but still that there would be a depletion under the gate also, na? So, but we have not considered that in this.
There would be a depletion under the gate at all times.
There is some VGS. I mean, there will be some kind of
yeah, there would be some depletion, but when so there would be a point where there would be no depletion also. So we are not really talking about whether there's a depletion there or not. What we are saying is that the drain voltage and the impact of drain voltage on the depletion layer starts to impact the barrier on the source side also.
So, sir, like it's like in short, you're saying that when in the short channel devices, when there is a change in the voltage on the VD, so that changes the depletion at the drain, but that also in effect changes at the source. So
it changes the barrier at the source, and therefore leakage current changes, and that is what is called as drain induced barrier lowering.
Okay. Okay.
So
Sir?
high drain voltage causes current to increase, and that is what you are seeing in this red region over here.
Sir?
Yes.
Sir, so now as someone already asked, so we were speaking about NMOS previously, and my NMOS will be off when my input will be 0.
Yeah.
Right, sir. So input is nothing but we are giving it to gate. So I don't see any kind of depletion region forming over there because my gate voltage is 0.
But the voltage that I have applied at gate is 0, but the doping that I could have done on the gate or the metal that I would have used for the gate can still pin it in such a value that there could be a depletion region.
Might be, sir. I'm not sure.
Yeah, you can study. So, bhai sir, this is all SSD. You can read that there, and you will find out. Okay. So now that was DIBL. Then there is another effect which is called as body effect, where we